Hello, this is the section 2.2 lesson. In chapter 2, we're going to start studying the idea of random variables in depth. Random variables are something that we introduced back in chapter 1, and they are extremely important because they form the foundation of everything we're going to do for the rest of the semester. You're going to get very sick of me saying the phrase random variables. In section 2.2, we're going to also introduce what we call the probability mass function. But let's start off by talking about what are random variables. Informally, a random variable is a rule for assigning a real number to each outcome of a random experiment. So we're going to do some sort of random experiment. With each outcome, we associate a real number, and that rule for assigning things is what we call a random variable. So a couple of examples. Suppose we randomly select a fish from a lake. Let the random variable z denote the length of the fish in inches. Okay, so here, an outcome to this to this experiment is a fish. The random variable is the length of the fish. That's a real number. Okay. Another example: a voter is randomly selected and asked if he or she supports a candidate running for office. Let the random variable w equal 1 if the person supports the candidate and 0 otherwise. So here, an outcome to this random experiment is a person. Our random variable is 1 or 0. It takes on one of those two values. So this definition 2.1.1 is a little more formal definition of a random variable. It's a little bit abstract, but it says let S be the sample space of a random experiment. A random variable is a function that maps that sample space over to the real numbers. Remember that this symbol here, this kind of bold case or script case R, stands for the real numbers. So random variable is a function that takes the outcomes, maps over the real numbers. The set of possible values of our random variable is called the range of the random variable. Range, same word that you used back in high school algebra when you first introduced functions. Range of a function was the set of possible outputs or possible values. No difference here. Okay. Now this definition is a bit abstract, so let's make some practical comments about it. Number one, a random variable is a function. Okay. It takes in an outcome from our random experiment and returns a real number. Okay. Number two, a random variable is not a probability. Okay. Random variable is not just another term for a probability. It's a completely different idea, but closely related. Okay. Number three, random variables can be defined in practically any way. Their values do not have to be positive or between 0 and 1 as with probabilities. Okay. Random variable could take on negative values, it could take on decimal values, it could take on numbers greater than 0, values greater than 0, a lot of possible ways. Now there are some limitations as to how we can define random variables, but we're not going to get into that right now. Okay. Number 4 is a comment about notation. Random variables are typically named using capital letters such as x, y, and z. And we'll use the random variable x a lot. Values of the random variables are denoted with their respective lowercase letters. Thus the expression capital X equals little x means that the random variable capital X takes on the value little x. So that expression capital X equals little x looks a little weird the first time you see it. We often think capital letters mean the same things as lowercase letters, but that's not the case here. Capital X is the name of the random variable, or the name of the function. Little x is the value of the function. Okay. Now, in this book, we're going to study two different types of random variables, discrete and continuous. Here in this definition, we define what a discrete random variable means. Random variable is discrete if its range is either finite or countable. Range is finite means that there's just a finite number of values in its range. Countable means that you could line up those values as like the first, the second, the third, so on and so forth. Now, chapter 3, we're going to study continuous random variables. We won't give a formal definition here, other than to say they're kind of like the opposite of discrete random variables, but that's not the formal definition. Okay. Now let's make an observation here about these random variables. The values of a random variable are determined by chance. Think about the fish example. We randomly select a fish from the lake, and therefore its length is random. Okay, we randomly select a voter. Whether that person supports the candidate or not is random. Everything is random. Okay, and so that means there's a lot of probabilities involved here. We want to describe the probabilities of these values, like with the candidate or the selecting the voter. We might want to know what's the probability that x equals 0 or the probability that x equals 1. Everything's determined by chance. We want to describe those possibilities or those likelihoods with probabilities. Okay, and so to do that, we're going to define this function, call it little f. Little f of little x equals the probability that capital X equals little x. Okay, now that's a rather short equation there, but rather complicated. So we're defining this function little f, and the input to this function is little x. That's going to equal the probability that our random variable capital X equals that value little x. And so this function is what we call the probability mass function, abbreviated PMF. Okay. So this is kind of an informal introduction to the idea of a probability mass function. Let's give a little bit more formal definition of this. So it says let x be a discrete random variable and let r be the range. The probability mass function of x is a function, little f, that's going to take those values of the random variable and map them to the real numbers. And it satisfies the following three properties. Okay, so let's stop right there for a second. So probability mass function is a function, meaning it's going to take in something and spit out something else. In this case, it takes in values of the random variable, which are real numbers, and then it's going to return another real number. Okay. But this is not just another type of random variable. It's a function that satisfies the following three properties. Number one, f of x has to be greater than 0 for all x in the range. So it's saying that this probability mass function can never be negative. Number two, if we add up all the values of this function over all possible values in the range, it should equal 1. Okay. The third property is really a description of how we're going to use this probability mass function. It says that if A is a subset of R, so if A is a collection of values of the random variable, then the probability that x takes on a value in that collection is equal to the sum of the PMF over the values in that set A. Okay. Now that definition is a little abstract, and so we're going to illustrate that in an example here. But before we do that, let's go to another definition. This is another term that we saw back in Chapter 1, the distribution. The distribution of a random variable is a description of the probabilities of the values of the variable. And this can be given in three different forms: a table, a graph, or a formula. And we're going to see all three of these different types of descriptions throughout the semester.